Hello students, welcome once again back to Mass Transfer 1. So where we are in the process of understanding the various methods of distillation. So this is the fourth session of the unit methods of distillation. So this is what you studied in the previous class. So in the previous class we studied about rectification or fractionation. So its principles of working, and also we studied how rectification is carried out in tall towers. So then we took up a method called McCabe-Thiele method that is used for studying the theory of the tray columns, that is involving the method used for designing the plate columns. So we derived enriching line equation, stripping line equation. So today we'll discuss about the feed condition to distillation column. So at what condition the feed enters the distillation column? In that discussion, we will come across a factor called Q factor, so which is used to describe the condition of feed that enters the distillation column. So then using Q factor and other assumptions, we will be deriving operating line equation for feed condition called feed line equation, which is also called as Q line equation. And then we have to learn to construct a feed line in the previous class. So like how we learned to construct enriching line and stripping line on an equilibrium diagram. So here we are going to learn how to construct a feed line. So the feed line position changes for different conditions of feed. So for what position um, we have particular condition of feed that is going to be discussed today. So then we have to understand the graphical procedure to determine the number of theoretical plates required by McCabe-Thiele procedure. So let us start with the condition of feed to distillation column. So you all know that the feed enters more or less at the center of the distillation column. So whichever plate on which the feed is introduced is called as a feed plate. So in the beginning itself I told you that feed may enter in a number of conditions, like it may enter like a in the form of a liquid, or it may enter in the form of vapor, or it may be a mixture of vapor and liquid. That is, partly it is vapor and partly it will be liquid. So at what condition it enters, uh, that also uh, depends upon the thermal condition of the feed. That is, at what temperature it is entering. So let us see which are all the conditions at which the feed can enter the distillation column. So it can enter in the form of a cold liquid. So cold liquid is the one which is at a temperature lower than its bubble point. So all of you know what is a bubble point. So if the temperature of the feed is entering, that is entering the distillation column, is less than the bubble point, it is a cold liquid. Then it is a saturated liquid if it is entering at its bubble point. Then it is a mixture of vapor and liquid. That is, partly it is a liquid and partly it is vapor if the temperature at which it is entering is in between the bubble point and the dew point. Then it will be in the form of a saturated vapor if the feed temperature is exactly equal to dew point. And it will be in the form of a superheated vapor where the feed temperature, that is the temperature at which the feed enters, will be higher than the dew point. So these are the 5 conditions of feed that enters to a distillation column. So let us now see how the different conditions will alter the vapor and liquid flow rates differently in a distillation column. So let us consider the middle section of the column like this distillation column. So this is the point where the feed is entering. So consider that your feed is for the time being mixture of vapor and liquid. So the mixture enters here. The vapor portion gets added to the vapor stream that is flowing in the upward direction. The liquid portion gets added to the liquid phase that is flowing in the downward direction. So here we have a factor called Q factor which describes the feed condition. See, so let us understand what is this Q now. So Q is a number of moles of liquid that flows in the stripping section due to the introduction of 1 mole of feed. That is, if 1 mole of feed is entering, that means if F is equal to 1 mole, then Q moles will be liquid portion, remaining 1 minus Q moles will be vapor portion. Okay, so since we have F kilomoles of feed entering as per our assumption, so the total amount of liquid, that is moles of liquid that flows in the stripping section due to the introduction of F kilomoles of feed will be equal to QF kilomoles of liquid, and 1 minus Q into F will be the kilomoles of vapor that is getting added to distillation column. So now this condition also alters the vapor and liquid flow rates. So suppose if the feed is entering as a cold liquid, so it will be at a temperature less than its bubble point. Okay, so under that condition, when it contacts the vapor, it causes the vapor to partially condense. Means some part of vapor at this location condenses due to the introduction of the feed at cold liquid condition. So the vapor flow rate decreases, but the liquid flow rate increases because there is additional amount of liquid getting added due to that condensation. So that is the impact if the feed enters in the form of cold liquid. So now if it enters in the form of a saturated liquid, so saturated liquid will be exactly at its bubble point. So we also have assumed that vapor will be at a dew point and the liquid that is flowing down will be at the bubble point. Okay. So here Q moles of liquid gets added to stripping section. So there is no vapor since it's all entirely a liquid. So vapor flow rate is not affected or is not changed, whereas the liquid flow rate slightly increases because there is additional amount of liquid that is getting added by the feed. So that is what is happening if the feed enters as a saturated liquid. Now, in the next condition, if the feed is entering as a mixture of vapor and liquid, so in that condition, both the liquid flow rate increases as well as the vapor flow rate because the vapor portion gets added to vapor stream and the liquid portion gets added to liquid stream. So that is a impact when feed is in the form of a mixture of vapor and liquid. So now, if the feed is entering as a vapor, is a saturated vapor, then that entire vapor gets added to vapor stream. So since it is at a saturated condition, so it does not have any impact on the liquid flow rate. Okay, so only vapor flow rate increases, liquid flow rate remains unchanged. Again, when the fluid enters as a superheated vapor, means this will be in the form of vapor at a temperature more than its dew point. So now in this condition, when it enters the distillation column, that vapor gets added to the vapor stream in the upper direction, and when it contacts the liquid phase at the feed plate, it causes some of the liquid to vaporize. That is, partial vaporization takes place due to the introduction of the feed. So as a result, the liquid flow rate reduces, but the vapor flow rate in the upper direction increases. So that is how the feed entering at different conditions alter the vapor and liquid flow rates at the feed plate, that is inside the column. Okay. So I hope all of you remember these notations. VL is the vapor and liquid flow rates in the enriching section. V bar, L bar are the vapor and liquid flow rates respectively in the stripping section. Okay, so let us now uh, use these notations to show how the vapor and liquid flow rates are changed. So here, since it's entering as a mixture of vapor and liquid, the liquid portion is getting added to the already coming liquid quantity of L. So L bar will be the sum of L plus QF. So that is equation number 8. So we have continued this naming the equations from the previous class. So because all this comes under the McCabe-Taylor method. So which we started in the previous class will be ending in today's class. Okay, so that numbering the equations will be continued from the previous class. So in the previous class, the last equation we derived was the equation of operating line for stripping section, which is equation number 8. Okay. So now L bar is equal to L plus QF. The next equation will be that of V. So V also gets changed because it is a sum of V bar plus 1 minus Q into F. So keep these two equations for further substitution in the feed line equation derivation. Okay, so let us now write down the material balance for A in the enriching section due to the introduction of feed. Okay, so Vy amount of A leaves the top of the column, so that is divided into dxt moles of A in the distillate plus Lx moles of A in the reflux liquid. So let this be equation number 10. Similarly, writing material balance for component A in the stripping section. It is L bar X, L bar amount of liquid goes out containing X mole fraction of more volatile component. So multiplying the two will give you amount of A that is present in the liquid going out from the bottom of the column, that is equal to, so V bar Y plus WXW, because this liquid is partially vaporized to create V bar vapors, so that is sent back to column, and the remaining is the waste or the residue that is withdrawn from the bottom as a product. Okay, so L bar X is equal to V bar Y plus WXW. Keep this as equation number 11. So adding the two equations, so L bar X plus Vy on the left hand side is equal to dxt Lx plus V bar Y plus Wxw. Okay. Now take all the terms that have X on one side and the terms which have Y on the one side. So keep this dxt and Wxw together on the right hand side itself. So that is how we can rearrange the equation. So shifting V bar Y to the left hand side. So Y is common, taken out. So then inside you'll have V minus V bar. In the same way, we should shift this term to the right hand side. So X is common, and in bracket you'll have L minus L bar plus dxt plus Wxw. Okay, so now if you look at these two terms, dxt plus Wxw is equal to Fxf, that is obtained from equation number 2. That is the overall material balance for component A. So we can replace that Fxf from equation number 2 in this equation by substitution. Okay, then the equation changes to, so y into V minus V bar as it is on the left hand side, and here x into L minus L bar plus Fxf. Okay, so now uh, we have this term V minus V bar L minus L bar in equation number 8 and 9. So we know that V minus V bar is equal to 1 minus Q into F, and L bar minus L will be equal to QF. So substituting this term and this term respectively from equation number 8 and 9 in the above equation, you'll get, so Y will be equal to Y into V minus V bar will become 1 minus Q into F is equal to X into L minus L bar will be minus QF. So substitute that, and Fxf, keep it as it is. So now here F is a term, and in both the terms on the right hand side, so F is a common term. You can take that F outside and get it cancelled with the F on the LHS. Okay, so you can eliminate F from the equation. Okay, so after eliminating F, what you have is Y into 1 minus Q on the left hand side, X into minus Q on the right hand side plus XF. Now shift this term to the denominator to get an equation in the form of Y is equal to F of X. So then the equation becomes Y is equal to, so here Q divided by, it will be actually minus QX divided by 1 minus Q. So if you take this minus sign inside the bracket, then it becomes Q divided by Q minus 1 into X plus XF divided by 1 minus Q. So you can write it down as minus XF divided by Q minus 1. So keep this as a equation number 12, which is called as a equation of operating line for feed or the feed condition. Okay. So now this is the final form of your feed line equation, also called as Q line equation. So this is a equation of straight line on a xy diagram, and the straight line will have a slope of q by q minus 1 and an intercept of minus x by xf by q minus 1. Okay, so now just like how we did in stripping line equation and enriching line equation, so if you replace this x by xf, okay, so then what happens? So xf here being common can be taken outside. Then inside the bracket you will have q minus 1 and also q minus 1 in the denominator gets cancelled. So as a result of which you will get y is equal to xf. So telling you that q line, just like your enriching line or stripping line, also starts from a point on the diagonal line which corresponds to y equals f value. So at a point say f that corresponds to xf on the x-axis as shown in the following figure. Okay, so the position of q line, as I mentioned already when we started our discussion, will be depending upon its feed condition. Okay, so that is what is shown in this diagram. Okay, so the q line starts from a point f on diagonal line corresponding to value xf. So these are the various positions of the q line for different conditions of feed. So let us now understand what this line number 1 says, what this line number 2 means. Okay, so the first one, when the feed is a cold liquid, value will be greater than 1. Okay, so cold liquid means it is entering with a temperature less than its bubble point. It tends to condense additional amount of liquid from the vapor. So due to its lesser temperature, so then the amount of liquid that flows in the stripping section will be greater than 1. 1 mole of feed enters, so that plus the additional amount of liquid added by that condensation. So Q value will be greater than 1 when the feed is a cold liquid. So in this condition, the slope of the feed line is positive as shown by the line 1. Okay. So this is a line, this is how the line gets positioned, that is a feed line, when the feed is entering in the form of a cold liquid or a subcooled liquid. So let us take up the second line. So whenever the feed is entering as a saturated liquid, Q value will be exactly equal to 1. So because whatever amount of liquid that enters gets added to stripping section. So if 1 mole of feed enters, then 1 mole of liquid flows in the stripping section. So Q value will be equal to 1. So when Q value will be equal to 1, the slope of the feed line. So you know what is the slope of the feed line? It is Q divided by Q minus 1. So 1 divided by 1 minus 1 is 0. So 1 by 0 is infinity. So the slope of the feed line will be infinity, and due to this, the Q line will be a straight vertical line as shown by the line 2. Okay. So let us look at the third position of a feed line. So whenever the feed will be a mixture of vapor and liquid. Okay. Here, uh, when 1 mole of feed enters the column, 1 minus, that is q moles of liquid flows in the stripping section. That is 1 minus q moles of vapor flows in the enriching section. So that means, so part of 1 mole will be the q value. That means the q value will be less than 1. So in that case, the slope of the feed line will become negative because the slope is q by q minus 1. So 1 divided by less than 1 value minus 1 will be a negative value. So the slope will become negative and the q line will have a position. So in between this vertical and the horizontal line. So that is the position of q line when you have the feed in the condition of a mixture of vapor and liquid. So when the feed is saturated vapor, so when it enters in the form of vapor at saturated condition, its temperature will be equal to dew point. So there Q will be equal to 0, means there is no additional amount of liquid to flow in the stripping section due to the introduction of 1 mole of it, because all 1 mole will be vapor that flows in the enriching section. So in that case Q value will be equal to 0, and as a result the slope of the feed line Q by Q minus 1 will be equal to 0. Okay, so d0 divided by anything is 0. So the feed line slope becomes 0. That means the feed line assumes a position of horizontal line that is parallel to x-axis as shown by the line number 4. So the last condition, when the feed enters in the form of a superheated vapor, the Q value will be less than 1. Okay, because superheated vapor will cause the vaporization of a part of the liquid coming from the enriching section into the stripping section. So the Q value will be again less than 1. So then the slope of the feed line will be negative again as shown by the line number 5. Okay. So that is how the different conditions of feed decides the position of the Q line on a equilibrium diagram. So now we have learned how to construct enriching line, feed line, and also the stripping line. So let us sum up all that together to study the graphical procedure to find out the number of theoretical plates required for a particular distillation operation. Okay, so you will require exact value of Q to calculate the slope of the Q line to construct a Q line. So if it is in the condition of a saturated liquid and vapor, then your Q line Q value will be fixed. That is saturated vapor Q value 0, and the superheated vapors Q value will be equal to 1. So that means in that two conditions you don't have to calculate the Q value, but in other conditions you require to, an equation to find out the exact value of Q. Okay, so first let us understand again the different conditions of feed by showing that position of the feed on a vapor liquid equilibrium diagram. It is a constant temperature, constant pressure vapor liquid equilibrium diagram. So this is a plot of temperature versus xy. The upper curve, you know that it's a bubble point curve. The lower curve is a dew point curve. So you know that any point below the lower curve is a subcooled liquid, and exactly on the lower curve it's a saturated liquid, and at a point in between these two curves it is a mixture of vapor and liquid, and at all points on the upper curve it is a saturated vapor, and at all points in the upper area, that is above the T versus Y star line, is a superheated vapor. Okay, so superheated vapor is represented by a point here, and in that condition the Q value will be less than 0. So if it is a saturated vapor, it will be indicated at a point on the upper curve. So in that condition Q value will be equal to 0. So if it is entering in that form, then calculation of Q is not required. So but anyway, if it is a superheated vapor, you require an equation to calculate Q. So mixture of vapor and liquid means the Q value between will be between 0 and 1. So, and it will be exactly that fraction of liquid that is present in the feed. So here also you need not calculate the Q value. So just by knowing what is a fraction of liquid in the given feed, you can find out the value of Q. Using that you can calculate the slope of Q line and construct a Q line. So then if it is in the form of a saturated liquid, Q value will be equal to 1. So here also we don't require an equation to calculate the Q value. So however, if it is in a subcooled liquid, the Q value is not known. It will be greater than 1. So exact value depends on exact temperature at which it enters, and also the condition of weight at that particular temperature. Okay, so you require an equation to find out Q in two conditions, that is in the superheated vapor condition, in the subcooled liquid condition. So let us now see which are all the equations that you can use to calculate the Q value. So if it is a subcooled liquid or a cold liquid, as I told you, the temperature of the feed will be less than the bubble point. So in that condition, Q value will be greater than 1 and it is calculated using this equation. Q is equal to 1 plus CPL into Tb minus Tf divided by lambda. So this CPL is the specific heat of the liquid, Tb is the bubble point temperature, Tf is the feed temperature. Then lambda is the latent heat of vaporization at whichever temperature it is entering. So if you know all these values that is obtained from the data, then you can calculate the Q value. So you can also calculate the Q value using this equation 1 plus Hp minus Hf divided by lambda. Hp and Hf are the enthalpy of feed at bubble point and at feed temperature respectively. Okay, and whichever temperature it enters, that is the Hf, and the enthalpy at its bubble point is Hp. Okay, so in the second condition, that is saturated condition, Q value is already known. It is equal to 1. You need not calculate here. So here the saturated liquid condition means that Tf, that is feed temperature, will be equal to Tb at bubble point. So if it is entering in the form of a liquid and vapor mixture, then the temperature of feed will be between the bubble point and the dew point. Accordingly, the Q value will be between 0 and 1. Okay, here also you don't have to go for a calculation of Q to know its exact value. So it is simply the fraction of feed which is in the form of liquid. Okay. In the next condition, that is saturated vapor condition, the feed temperature Tf will be equal to Td. So that means it enters in the form of a saturated vapor at its dew point. So for this condition, Q value will be equal to 0. No requirement of calculation. So in the condition of superheated vapor, the temperature of feed will be greater than the dew point. So here the Q value will be actually a negative value. It will be less than 0. So here the Q value is calculated using this equation. Q is equal to CPV Tf minus Td divided by lambda. So CPV is the specific heat of vapor, Tf is the feed temperature, Td is the dew point temperature. Also this is equal to Hf minus Hd divided by lambda. Hf is the enthalpy of feed, Hd is the enthalpy of feed at the dew point, lambda is the latent heat of vaporization at temperature Tf. So that is how we can estimate the value of Q before you construct a feed line equation. So to calculate the slope of feed line, you require the value of Q because the slope of feed line is equal to Q by Q minus 1. Okay, so this is the graphical procedure to find out the number of theoretical or ideal stages or plates that are required for a particular distillation operation. And this is a procedure proposed by McCabe method. The procedure is simple. So first you have to construct an equilibrium diagram. So X versus Y plot. So draw a diagonal line and an equilibrium curve using XY data. So this you have already practiced. So after you construct equilibrium line, so locate point D, F and W by knowing the value XT, XF and XW. So corresponding to these three values, so we have located 3 points D, F and W. So from D, draw a straight line with the slope xt by r plus 1. So if you know the reflex ratio for a particular distillation operation, you can calculate xt by r plus 1. So mark that value on the y-axis and that value point will be joined to point D. That completes the construction of enriching line. Then you have to construct the feed line using the value q by q minus 1. So once you know the Q value, you can calculate the slope and construct the Q line. The next part is the construction of stripping line. So once you construct the Q line, so this line, if it is extended, so it will cut the enriching line at a point. So that is your point C. So then join this point C to point W. that completes the construction of stripping line. So once the construction of operating lines is over, the last step in the procedure is to make stepwise construction between the equilibrium curve and the operating lines, starting from point D and carrying out the construction till you cross point W. Okay, so I'm starting from here. From point D, draw a straight horizontal line. When it touches the equilibrium line, from there onwards, draw a vertical line. Again, when the line touches the enriching line, so from that point, make a horizontal line that meets at a point on the equilibrium line. Again, draw a vertical line. Like this, continue horizontal vertical line construction till you cross point W. So that is called stepwise construction. Then count how many number of steps you have made. So in this example, I made 1, 2, 3, 4, 5, 6, 7 steps. So that is your answer. So the number of theoretical plates required plus 1. 1 is meant for the reboiler because we assume that there is a vapor liquid contact occurring at the reboiler also. Okay, so this number of steps will be NP plus 1 equals 7. So actual number of plates required in a distillation column NP will be equal to 7 minus 1, that equals 6. So feed plate is third from the top. So if you want to locate the position of the feed plate from this procedure, so see whichever step is crossing point C. So here, this is the first step, this is the second, and this is the third step. You can see that the third step is the one which is crossing the point C where all the operating lines are coinciding. Here, that third plate is the feed plate, means the feed will enter the distillation column exactly at the third plate from the top of the column. So this is what is known as graphical procedure to find the number of theoretical or ideal stages. Okay. So just look at the points or the steps in the graphical procedure. First step, draw the equilibrium curve and the diagonal line. Second step, fix D, F and W on the diagonal line corresponding to XD, XF and XW respectively. Calculate XD by R plus 1 using this as the intercept. Draw the enriching line from point D. Next step, from point F, draw a straight line of slope Q by Q minus 1. So this line will cut the enriching line at point C. Then join W and C to construct stripping line. Then starting from D, make a stepwise construction between the equilibrium curve and the enriching line as shown. When point C is crossed, switch over to stripping line and continue till point W is reached. Okay, so you're starting stepwise construction from here. So once you cross point C, the stepwise construction will be switched over to the construction between the equilibrium line and the stripping line. You should not take the enriching line from this point onwards. Okay, so it will be between the equilibrium line and the stripping line. Okay, then count the number of steps made. That gives the number of ideal plates required, NP actually, including the reboiler. So that will give you NP plus 1. So the step which crosses point C is the point of intersection of all the operating lines, gives the position of the feed plate. So whenever whichever step that is crossing point C, that step is the feed plate for the given situation. Okay, so with that, let me conclude the present session. So this is a recap of what we studied in the today's class. So we discussed about the various conditions of feed to distillation column, and we understood what is a Q factor, what is its significance in continuous distillation operation. So what is a feed line equation, how it can be derived, and how using which you can construct the feed line on a equilibrium diagram. So we also understood the different positions of the Q line or feed line for different conditions of feed. So then we discussed at the end the graphical procedure to determine the number of ideal plates required. Okay. So in a McCabe-Thiele method, this is a set of multiple choice questions. So let us go through them to check out our understanding level. In a McCabe-Thiele method, if F equals moles of paper present per mole of feed, then which of the following applies to a feed at dew point? So F equals 1, F is less than 1, F is greater than 1. Is it having a value between 0 and 1? See, it is given that F is the moles of vapor present in the feed that is entering in 1 mole per second per hour. Okay. So, if F is equal to 0, then the feed will be at its dew point. So, because the entire vapor will be added to the vapor phase in the enriching section. So there is no liquid flow in the stripping section due to the introduction of 1 mole of feed. So all that is entering in 1 mole per hour will be added to the vapor phase. Okay. So first answer is the right answer for this question. So when the feed to a distillation column is saturated vapor, the slope of the feed line is 0, unity, infinity, none of these. So whenever the feed is a vapor in the saturated condition, the slope of feed line will be 0. Okay, so that is the right answer for this question. When the feed to a distillation column is a saturated liquid, then the slope of the feed line, is it 0, is it unity, is it infinity, is it none of the above options. So, so 0 is the slope when it is in the saturated vapor condition, and in the saturated liquid condition the slope will be infinity. So option C is the right answer. The slope of the Q line is determined by reflux ratio, plate efficiency to be achieved, thermal condition of the feed, relative volatility. So which of these factors decide the slope of the feed line? Okay. The slope of the feed line, if you can remember, is equal to Q by Q minus 1, where that Q is a factor that describes the feed condition, that is the thermal condition of the feed. So the slope of the Q line is determined by thermal condition of feed. So third one is the right option. The Q factor is defined as the number of moles of dash due to introduction of 1 mole of feed. Options: liquid that flows in the stripping section, vapor that flows in the rectifying section, vapor that flows in the stripping section, liquid that flows in the rectifying section. Okay, so it is nothing but Q is the moles of liquid that flows in the stripping section due to the introduction of 1 mole of feed. So that is according to the definition of Q. Option A is the right answer. So thank you for being a part of this session. I hope all of you have understood the concepts clearly. So please go through the notes as well as the YouTube links that are given. So in which the topics that are discussed in these particular sessions have been explained through videos or animated videos. So with that, we are ending the class. So let us again meet in the next class.